Right, actually, so I just want to do a couple of things here. Introduce this idea of thinking about these shapes in 3D, um, or 2D in this particular case, as graphs. Okay, so on the left here, what I've got is a picture from Wikipedia. If you search for Circle of Willis, that's one of the illustrations that you've got. Sort of quite a good reference. There's probably a lot more detail than we actually need. But it shows you the different major vessels, right? So the and how they're connected in this circle of Willis. So you can look around there for a little bit more detail for the ACA, MC, and PCA, maybe the three major divisions. But the sort of idea I want to introduce to you is this idea of a mathematical graph. Okay, so you can also look that up on Wikipedia or in a textbook if you've got one lying around. But sort of a quick and concise summary is that in discrete mathematics or in computer science, a graph is constructed of having certain nodes, which are often symbolized as circles or squares or something like that. And these can be connected or not connected with edges. Okay, so for example, this is an example of a very simple graph that has node A and node B connected. In some versions, if you're interested in how things are flowing, for example, you could even have a directed graph, right? Meaning that things generally flow from A to B, or another graph would be, which looks the same, but would be different, where things flow from B to A, or you could even have bidirectional things. So for example, if you wanted to illustrate, say, populations from, exchanging between A and B, something like that, you could have arrows going in both directions. Okay. Now, sort of the reason this might be interesting or useful in our particular case is because there's obviously a complicated geometric shape, but if you're just trying to establish whether a particular part of the circle of Willis is intact, what we really want to do is we want to figure out whether the sort of the essence of the shape looks something like this, coming back, maybe like this, and graphs going off. And so you could imagine having a node at each of those locations here, and edges that connect them. You don't actually care whether these individual distances are a little bit different. What you care about is whether this whole shape is intact or not. But you could imagine that in a case where maybe there's a disconnection between some of these things, this graph would actually look quite different, right? So maybe it would look something like this in that particular case. And there's no connection between these two things here. So there's some nice mathematical tools for checking whether these differences exist, or if you don't want to go that deep, even just visualizing what is the essence of the connections might be sort of a useful way to go. And this is the general idea that lies at the heart of having this skeleton version of the image that we are segmenting. Right, in this video I want to come back to this idea of analyzing the shape of this skeleton that we can produce with this skeletonization code. And so what I want to do first is just rerun the skeletonization on this vessel probabilities image that we have, right? So what is the point of that? We're trying to extract the fundamental shape, or sort of the spine, I guess, of the 3D structure that's there. And so between recording these videos, I've played around with this a little bit, and I'm actually going to be a little bit more permissive in the amount of stuff that I allow in. So there's a step here where we turn this probability image into a binary image, right? Is there something present, yes or no? And previously I used this threshold of 50. I think I want to change this to 25, so I think it was 50 before. The other thing, if you're starting up again your MATLAB session, you might want to make sure that the skeleton 3D function is actually on your path, right? So if you type which skeleton 3D, you actually get an answer back. If it can't find it, then obviously your paths haven't been set correctly, which might give you some errors. Okay, so this is the this code which I will make available in our shared Teams folder as well. But it's essentially just a reworked version of this test script that ships with the functions, and all I've done is attached data loading before, so I haven't really done anything else. Okay, so I'm going to run this by pressing the play button, and it will actually take about 15 or 20 seconds to do these calculations and the rendering, so I might speed this up a little bit in the video so you don't have to wait around for that. Okay, so here it goes. All right, so actually that took quite a lot longer than the 15 seconds I had with the previous number, but that's because there's more stuff involved here now. A lower threshold means a larger number of voxels to process, and so I guess skeletonization takes a bit more time. But this actually results in quite an interesting shape here, right? So you remember what's being plotted here is in this gray shape, sort of a transparent view of the vessel, in this particular case, right, from the actual template, not from the original data set. And in red, symbols that show this skeleton, which is a 1 pixel wide thing at the center that shows the shape of this particular object. Okay, and it's kind of cool, right? So you can see that there's this structure of the circle of Willis, which looks disconnected at the probability values I've taken. But for visualizing how things are connected, actually, we could use this as quite an interesting starting point. Okay, I'm going to close the figure window down for now. And I will look in the workspace what's available here now. There's quite a few variables that get created. So, as you may remember, if you run things as a script, then the variables stay in the workspace. What I want to do is the skeleton, which is stored in the scale variable, is something that we want to use in our next step. So I'm going to save that out. Okay, so one way you can just do that is use the save command and say save scale. If you do that, actually use -5 scale. No, actually that saved all of them out, so that's not really what I wanted to do. So let me just repeat that step. So I'm going to say save, scale.mat. I don't want to save out the whole workspace. I only want to save out this variable called scale. Okay, should be much faster. So if I now do who's -file scale.mat, it should only contain this one variable. That's all we need, really. Okay, so we can save this around, which will save us the step of running this particular script every time we want to do the next step, which is actually looking at the graph visualization thing. And the other thing I can do is I can now actually clear all and close it all and get rid of the workspace. Okay, just type home here. Now in the next step, I'm going to use the prepared script that they already gave us for looking at this other skeleton and visualizing it in graph form, and we're just going to transplant in our data set that we have. Okay, so I remember, because I looked it up just a minute ago, that this is called scale to graph 3D. Okay, and I'm going to once again save a local copy for us here. So I'm going to save this as angio Skeltograph 3D, and I'm going to save it in my current folder, so we have access to it later on. So this is in my MATLAB folder. In MC project inside the skeleton folder. Okay, let's save this here. Turning graph skeleton into graph, not the other way around. Okay, so now I can say DS 2027 based on example from GitHub repo this code. Okay. Again, I'm not going to do clear all, close all in the script. And I'm actually going to start using these double percent signs to actually try and work through here. So the question is, will load skel work? Well, if there's a file called skel.mat, which we now have, that should work. Okay, so rather than using their prepared skeleton, we're now actually going to load in our skeleton from the MRA dataset without having to do any changes. Okay. So these next 3 lines of code, they just figure out what is the size of this data cube in the first, second, and third dimensions. Okay, so make some comments here. Get size, get sizes of the 3D image. Let's see what's here. There's some initial step making this skeleton into a graph. And another step where there's a second skeleton. So I think this basically goes through and just double checks that we have the best possible version of this graph that we can get. Okay, so we can dig into some of the details here. I'm not going to actually change any of that stuff, so let me just try and run this and see how long it takes. That was pretty quick. Hopefully this will have created some intermediate variables here, yeah, including a whole bunch of stuff. And we can just try and visualize them now. Okay. So I'm going to just run this last cell. So visualization, so this typed visualization step. Okay, figure, make sure it stays on. It's going to put some stuff down by plotting things in 3D in different colors. And either showing branches, branch points, or link points in red. Okay, so this is basically a complicated looking bit of code, but we can probably try and unpack this if you want a little bit more. Let's just see whether this actually results in some figure here that we could use. And sure enough, we get this sort of interesting, complicated looking thing, which looks like sort of a network graph. And so the question is, what does this actually represent and mean? So if I rotate this around, hopefully you'll be able to see and recognize some structure here, which is this network representation, where different points in the skeleton are being represented as nodes that are linked by different things here. Okay. And you can see that this might be a very useful way for trying to analyze how these connections are being represented. Okay. If you want to actually understand how the information about this graph is stored in terms of vertices and nodes. You need to have a look at the documentation of the code here and probably do a little bit of reading up about how graphs are being represented. It looks like there are 239 nodes or around 200 nodes. So what do they look like? They each have an index, a bunch of connections, and so on, and a center of mass in X and Y, which you can look up what that is. So let's, for example, look at the first node. Has one link, is located at X, Y, and Z, 145, 147, and 20. Right, so these would be in voxel coordinates. And so for each of the nodes in this graph, there's going to be one description here like this, whereas the links, there's 191 of them. If I look at one of them, you can see that it goes from node 1 to node 91, and it will have some other information about how it is connected through this particular graph in what looks like sort of linear index in this particular space. This is all probably a bit more complicated than you need it to be. One thing you could explore is, how does this graph change appearance? So first of all, you could get rid of some of the symbols or change them to be slightly more visually appealing. You could ask the question, how does this connectivity of this particular graph change as you change the skeleton from which you make the graph in the first place? Okay, so in the first step, I said I was going to be a little bit less conservative. So you can imagine if you're being more conservative and throw more voxels out, things will be more disconnected. And you could try and visualize as a sort of a methodological step, if you're interested in visualizing the connections of the circle of Willis, as you become more and more conservative, how does that affect the connectivity between the different nodes? So that might be a useful and interesting thing to explore. Another thing you could do is, this might be another way of identifying different sections in here. Have a round, think about it. Maybe even see whether you can visualize some of the original image data that goes along with this by adding image slices to this particular plot. So I know this will work quite well. So as long as you additional visualization, make sure you hold on, and then use the command slice to actually plot the original data set, which you will have to load in right from the vessel probabilities file, and see whether you can add them maybe at the mid-sagittal or mid-coronal or mid-axial slices for making another kind of cool visualization and trying to merge these things together. Okay.